Joel is actually one of our sponsors, so we are very thankful for our sponsors. The next speaker is John Moncur, and he is from SpectralWorks, which is also one of our sponsors. So thank you for sponsoring this event and make this possible. John, the floor is yours.
Good morning. I presume everybody can hear me. Thanks very much for the introduction and also the opportunity to present here. This is crackling a little bit. Chromatographic and statistical methods. My chromatography for GC started with packed columns, and that kind of shows how long ago that was. It then moved on to glass capillary columns, these 50 or 100 meter rolls of glass that today now you snip the end off a fused silica column. To snip the end off a glass column, you needed a blowtorch and a lot of luck because it was just hard work. Then fused silica columns came on board, so much better, and really are now the gold standard of what we use. So that's the chromatographic side. I'll try and explore some of the sort of peak detection type of things that we'd be doing on that. Excuse me. Statistics, audience participation. Raise your hand if you know what this is. Okay, actually quite a small number. It is, of course, just a simple calculation of standard deviation. The vast majority of people here accepted it and accept it today for what it is. We don't have to worry about statistics. Statistics have become commonplace now. So, let's look at the problem that we've got. Capillary GC is, again, now an accepted type of acquisition and processing. Not particularly complex now. We understand all the principles of chromatography. People are familiar with it. They've got a lot of experience. We understand the sample prep required for GC. Software, everyone seems quite happy running the software and getting the data from it. And it's an automated system. We can have open access GCMS. And basically, it's accepted. Let's move on to the 2D GC. It's complex in people's minds. The principles of chromatography and MS remain the same. Training and experience, people are often frightened of it. There's a talk or a guided discussion this afternoon about trying to get people more trained and involved in 2D GC. What about training in statistics? Do we need it? Most people just use it. Sample prep, we know about it, it's the same thing. Maintenance, small changes can make big differences to your chromatography. Software, I think the first two talks yesterday both came up with the fact that software is a limiting factor as to how people perceive 2D GC. And automation, I think we had someone again yesterday or this morning saying that they've actually now introduced 2D GC to the chemists that don't have to have particularly expertise at it. And you've got underlying all of this. Let's go back to statistics again. We're doing peak detection. We're doing ion statistics even when it just hits the detector in the mass spec. They're doing centroiding. All of this is being accepted as, this happens every day. We're happy to have it. I'm going to really skip through the advantages of 2G GCMS. I'm sure everybody's been either at the workshops or know it very quickly: enhanced separation, peak capacity, sensitivity, comprehensive analysis, characterization, all of this sort of stuff. But I realize that we're short of time this morning as well. Now, We do chromatographic deconvolution based on sort of one-dimensional GC. And the idea is that we try and separate based on our MS information that we get. So we're doing chromatographic deconvolution based on peak start, peak end, peak apex, peak shape on the different ions that we see. You still require this in 2D GC. Although the separation is potentially a lot better, then you still have a requirement, or makes it more robust to be able to have this chromatographic deconvolution. We determine which masses belong to which particular peak, and we can do this on the 1D and the 2D types of columns. And we're not the only people that do this. Chromatographic deconvolution is available. So the effects of closely eluting components, we still have that requirement. In one dimension, you've got resolved components, partially resolved, and unresolved. If we've got the mass data, even if you don't, you can do the resolved and partially resolved. If we have the mass data, we can actually resolve components that are very closely eluting. We can sometimes do it with them absolutely co-eluting, but that would depend on peak shape, start and end that we're able to determine. Same thing happens in 2 dimensions. Here we can see we've got resolved peaks in 2 dimensions. We've reconstructed the 1-dimension chromatogram at the top. We can get component 1, component 2, and we have the various slices that we get from that component reconstructed into the 1D component. We can look at component 2 slices as well, so that we're able to differentiate them from the 1 dimension. When this goes to closely eluting components, we can still do the same thing in that we see the 1D component slices and the 2D component slices. So what does this look like with these slices taken into effect? We keep going on about statistics. We use statistics really very badly. We're very brutal, particularly in biological sciences, where we've got restricted numbers of samples. We don't have the idea of replicates, anything like the ones that we should have. But if we look at, say, treating 1D and 2D peaks in a similar way, these are obviously very different acquisitions. The first one is a 1D GCMS chromatogram, and the one below it is a reconstructed 1D GCMS chromatogram from 2D data. From this, you can actually see we're losing some of the primary resolution in that second chromatogram because the modulation time is too long. In this particular case, it was 8 seconds. And we're actually beginning to lose resolution on the first dimension. But we can plot this in our normal contour plot, and we probably find that we've got 2 or 3 times the number of components that we're able to split. Now what we do is we deconvolve these, we do the peak detection, we put them all back together again, and we actually get peak components. So we're treating it chromatographically. We're not looking at blobs, we're not looking at anything like that, we're looking at the actual chromatographic spectra. And if we look at what we can do with it, we treat it in exactly the same way as 1D. We can do our NIST searching, we can do target component analysis. We can do that in the first dimension, or the second dimension, or in both dimensions. I wouldn't necessarily recommend doing it in the first dimension, as you can get thousands of samples across there. We create our 2D components with quite stringent matching criteria, like the NIST format. But once we have that in the second dimension, we can relax those matching conditions to match each of the slices so that we actually build our component together. Typically, we'd like to see, well, as many slices as possible across a 1D peak, reducing modulation times to like 2.5 seconds, means that you'd be going to be able to get sort of peak widths of 5 seconds in the first dimension, matched quite well. So you can see here, this is an example here that we've got of how the 2D components are created from the 1D ones. The blue lollipops are one component, the orange lollipops are another component in the second dimension. Now, let's move on to the statistic proper. This is the kind of PCA analysis of 3 whiskies, very close to my heart. And what we see is obviously the statistical PCA separation. We're only looking at 3 replicates, which is not great, but it's there. What we have is the ability to actually interact with these PCA plots. Click on a sample, and it'll tell you which sample it is. Click on a loadings plot, on the loadings plot, it will tell you which component it is. It will actually give you, it also links through to the MS data that you can look at the spectrum itself. And then, if you're looking at a difference here, look at the box plot at the end. You can see very, very quickly differences statistically from each of the samples that we're looking at, each of the categories. So it makes it something that's very presentable. You said about you presenting it to a naive audience. Which one's higher? As a jury, I think you'd have to probably agree that the one on the far right, the Oban whiskey, has a higher level of that particular component in it. Press the wrong button. There we go. Statistical processing, we can go further and start looking at our volcano plots, the probabilities that we're seeing between them. The ones in grey are not statistically significant at p.05. We can filter them out because they're not really going to be of interest to you. And then that will just actually leave you with ones that are unique to each one and ones that are actually significantly different between all of them. And again, depending on what you look at, you can see that you've got very much higher levels in the third category of the open sample. Right, I'm rattling through this. In conclusion, the technology is undoubtedly more complicated. We know that. But it is becoming more and more routine. I think people are getting familiar with that. Chromatographic deconvolution is still a viable technique and will help with 2D GCMS. The data processing from GCMS, as we can show end-to-end statistical analysis, is exactly the same. So you can actually almost take the fact that you're doing 2D GC out of the equation and present the statistical conclusions. 2D GCMS is only part of a solution. Remember, always, and a number of times I've seen this and it's been terrible, think of the objectives that's going to be done and the initial experimental design. Because you can have the best chromatography in the world, but if you've got a poor experimental design, you're going to show nothing. Thanks very much to MDC. Thanks to Chip Cody up there from jail for some of the data. Thanks to my colleague Scott Campbell for actually doing most of the coding. And thanks to you for listening. And I'll leave you with the thing that you want to do. You can ask questions. But unusually, I'm going to actually ask you a question. What do you think are the potential developments that will advance adoption of the 2D GCMS? It's a rhetorical question, but think about it. Thank you for your time.